Is Paige Allen, and today I'll be talking about Physics 2211 Lab 2 called Projectile Motion. Just before we get started, a little intro. We will be talking about the purpose, procedures, results of the lab, and then some question and errors regarding the overall concept of the lab. So the purpose of the lab was to record and observe an object thrown like a projectile and compare its behavior to a computational model of a perfect projectile motion. Then we created a second computational model that actually took into factor real-world measurements. So in this case, air resistance or drag force. The system that we used for our experiment was a paper ball, which was the object that was thrown. Then the surroundings around it would be the room, the air that was contained in that room, and the table, which we considered our ground zero level. To be able to track our positions, for the observed, we use an app called Tracker, and for the predicted, we use a software called GlowScript. So just some key principles before we get started to let you know how this lab should turn out. On the left-hand side, I have some kinematic equations relating to Newton's first and second law. If we look at the second one, V final equals V initial plus AT, where A is equal to F net over M. In this case, gravity, negative 9.8 meters per second square. You'll notice that the only thing changing the velocity would be gravity times time. V initial stays the same, regardless. So, as time goes on, that constant, gravity times time, is going to increase to a point where V initial is going to become equal to gravity over that given time, and the velocity is actually going to be zero. At that moment, the object stops. And then from there on outward, AT is going to be greater than V initial, and the ball is going to continue decreasing velocity or falling. This is what we call free-falling objects, because no other force is being applied at that given moment. And you will see on the graph on the very top right that you start off on a positive value until it decreases and slows down to a velocity of zero, and then it speeds up and continues going negative. This will change our graph in a sense where when you look at the position final time, final compared to the initial, it's going to create a very lopsided effect where it's kind of an upside down parabola. And you'll notice that at each of these given moments, so like this first initial velocity compared to this final velocity once it hits the ground, they are actually equal in magnitude, but opposite in direction, until it reaches, like the second one, you'll notice that tangential is also the same, but different in magnitude, until it reaches that zero. So to be able to track our observed data, you can see right here, we recorded a video of us tossing the ball, and we made sure that our axes, these purple two lines, were aligned with the table. At each given point of the ball, we tapped at its center, until we got a really nice looking parabola shown with all those red dots actually. And you can even see that reflected in the Y position over time graph on this right hand side. For our computational, we changed a few factors. So of course we changed the ball's mass. We made sure that initial position was actually equal to the first two positions, the difference between them, that we found in our tracker data. Then with the velocity, we used those same differences in position and divided it by the respective times that they had. And that was what we were given here. I made sure to include the 0.377 and the 1.779. So in our second part, we made sure G equals gravity, and B, which would be our drag force, should be zero at this moment, first when we start. And of course, the net force is going to be gravity plus F drag, but for our first one, it's only going to be gravity considered since B is equal to zero. And then we had to update the velocity and position based on those kinematic equations used before. So this is what the computational model should look like. And on the right-hand side, we can also see a graph that was very similar to the one in the observed graph. So right here, I'm here showing you both of them at the same time. And you can actually see that for the observed data, the ball went quite farther compared to the computational data, where the computational data actually ended shorter. And then we tried changing the drag force to a factor of 0.005, which is this green line. And you can actually notice that it's very similar to the observational data. This is most likely because in the real world, there was drag force. And when you consider that, the ball actually stays in the air a little longer compared to if only gravity was there. Sources of error. Well, firstly, tracking, so the calibration of the scale was very difficult to see where that meter stick was. So when I had put in what the distance was, it could have been a lot greater or smaller than what was seen. The ball wasn't crinkled entirely into a ball shape. Of course, some of the surface area was a little off just because it is not a perfect sphere. So there could have been a lot more drag happening than what was predicted. Of course, you would kind of have to compute that, and I did the best I could to compute that. And then, of course, for data sorting, separating the columns into the data into columns was a bit difficult. Just because of how my software worked, and it resulted in some of them not being positioned properly and could have had some mechanical adjustments needed. So quick question and answers. Do any of the models predict a terminal velocity? So terminal velocity is the maximum speed attainable by an object as it falls through a fluid. In this case, fluid is the air. So this would actually happen where the forces are balanced, where force of gravity is equal to the drag force. You'll notice at this point, the velocity actually kind of tapers off into a constant. And that's when terminal velocity happens. This is considered when we were doing the predicted computational model. And actually, this was probably reflected in our observed data as well, because drag force should have been considered. The second question is, if the object were initially thrown straight up at the same initial speed, would it take longer to reach the ground? So right here, I decided to use the position update formula, where y would equal the initial delta t minus 1/2 g gravity t squared. In this case, I moved the variables around until I got that t equals 2 times the initial velocity over gravity. If you're considering a projectile that is thrown at an angle versus considering up, when it's completely up, it is perpendicular to the ground, which is 90 degrees. And of course, the sine of 90 is equal to 1. So you would have the entire velocity showcased. Whereas if it's thrown at an angle, you only have a fraction of that velocity, which would mean that the time is actually faster if it's thrown at an angle, while if it's not thrown at an angle and just straight up, it's going to be slow.